I'm in Hideo Mabuchi's lab, and my research is numerical, theoretical, on finding a scalable approach to designing quantum feedback circuits. The main message I'm going to convey today is to tell you how great quantum feedback networks really are. And I'll show you also how to work with them most easily. So the outline of my talk is I'll provide some motivation and background, and then as another part of the motivation, a real example from my own work that I think will exhibit the complexity of the models that we're dealing with and why a lot of automation is necessary to work with them in a way that is not too tedious. And then I will show some particular steps in what our typical workflow looks like. So first, how we specify quantum feedback circuits through this language that we derived off VHDL called Quantum Hardware Description Language. Then show the package that I wrote to do the symbolic analysis of the system. And finally, show how that interfaces with a numerical backend called QTIP, which some of you might already know. It's actually written by a former participant in Praxis 2 years ago in Tokyo. I think he wasn't officially attending, but he was there. And then finally, I'll just show a little outlook on what I'm planning to do in the future. And I wrote a little tool that makes the schematic capture less painful. So the main motivation is that our research is on coherent feedback networks, where I say coherent and not necessarily quantum, because we're working at different energy scales. So we're both interested in the very low few photon regime, but also the higher energy scales, because those are currently more realistic to actually build devices for. And so what's nice about SLH, or actually I'm getting to that soon, but what's nice about SLH is that you can start from a pure quantum description, and if you're not dealing with qubits, it's very easy to go to a classical description from that. And so that provides a really nice transition. So we're trying to come up with ideas not just for individual components, but also for whole networks that do interesting things that might have potential applications even for industry, information processing applications, signal processing applications that in some way have to, of course, beat electronics. So they have to be either at lower power or they can be used in situations where electronics might not be used or cannot be used well. So to do this, we're developing a lot of engineering intuition and reusable abstractions in designing the network. So stuff like how to construct an amplifier from different models, or how to construct something that oscillates, and so forth, like in electronics, really. And as I've already mentioned before, SLH really is the natural framework for doing this work. Because, as I said, it extends from quantum, and you can derive semi-classical models from it, which is probably much harder to do the other way around. And finally, I want to show you how to make the design analysis less tedious if you have good tools. So just further motivation, why are circuits interesting? Because a lot of people here seem to be working with single devices or doing metrology, and so for those people, probably preaching to the choir, but well, they're a super powerful design abstraction. They allow you to compartmentalize, to reduce by thinking about little boxes where some of these have a certain task, and then you put them into a bigger box that has a new task, and you can abstract away all the details. They're a visual tool allowing us to interact with them with more of our thinking than is involved if we're just doing math. And they allow us to take out a component and plug in a new one, so you can very easily do incremental or iterative improvements to your model, but that's only true if after you do a change, you don't actually have to do 2 hours of math to rederive the new model, because that kind of gets in the way of your flow, I'd say. The necessary background theory for working with these models are first quantum Markov models as developed in the whole QSDE formalism, Hudson Parsatharati. Then, of course, the Goff-James circuit algebra and the SLH formalism, which most simply put really tells you how to do this. If you have 2 quantum systems or 2 quantum input-output systems, Q1 and Q2, and you just want to bring them together without interaction, you do this with the so-called concatenation. If you want to feed one quantum system's outputs into another without reordering them, you do the so-called series product. And it's usually written from right to left because that is how the matrix multiplications work out. So it makes it a little easier to translate between the math and the notation. And then you can do feedback operations. And really, like, you only need the outer 2. And this one's a special case of those, but it helps in the thinking. Like, if you can write things in series, it's easier to reason about them. And then finally, I won't go too much into that because there's going to be a talk actually next Thursday. What's important for our work is also how to then derive semi-classical SDE approximations, which are technically not really quantum anymore because they can be simulated very efficiently. But that is also their huge advantage. So this allows us to deal with networks of actually hundreds or thousands of components, which we couldn't do with a full quantum simulation, obviously. All right, so a quick SLH crash course. I'll give it as an example just what models look like, and then in a second I'll show you how my code could be used by you for actually learning how to manipulate them. So this is a Kerr nonlinear cavity with a single mirror, and that's kind of a trivial example, not trivial, but the scattering matrix for this thing is just a single number because you have only a single input-output channel if you just have one mirror. So the scattering matrix is a 1, which means the direct scattering of light happens without any phase shift. Obviously, when you take the cavity dynamics into account, you do end up picking up a phase shift. But that then only gets modeled through the internal degrees of freedom, and the coupling operator describes how the external field couples into the system. Or maybe rather how it couples out. That's a better way to put it. And then the internal Hamiltonian, which here consists just of the frequency, the energy of the oscillator. And I've added a chi nonlinear term because that'll be helpful later. For those of you that have not seen chi nonlinear models before, they're one of the simplest nonlinear cavity models because they are nonlinear, but they can also be written down with a single mode. And most other nonlinear models that you could write down. So this is actually a so-called chi3 nonlinearity, but a chi2 nonlinearity would involve at least 2 different modes. So this is, I think, one of the simplest types of nonlinearities. And what it really means is you have an intensity-dependent detuning of your system. So how much power you put into your system will affect where its center frequency lies. Okay, that's the most important thing about Kerr models. And then 2 other examples that I think are great at explaining what SLH, what the different objects stand for, are a coherent laser displacement or laser source, which you can just write down as this. So it also has a simple scattering matrix, but it has a coupling vector consisting just of a number. And so I think in general, you should always think of the elements in the coupling vector as the outputs of your system. So the output processes, or if you take the expectation values and the thing coming out is pretty coherent, then it's the coherent amplitude of your output state. And then finally, the beam splitter element, which is the first element that has a non-trivial scattering matrix. And this is just one example of a beam splitter. The restriction on the scattering matrix is that the entries have to be numbers or operators on the system's Hilbert space. And it has to be a unitary matrix. So with the basic component models, you almost never end up with actual operators in the scattering matrix, but you can achieve those models by doing things like adiabatic approximation by applying those to certain systems. I think if you look at the QEC papers of our lab that Joe authored, there are some pretty good examples of that. And then the most important thing about SLH in the circuit algebra is that it's closed under circuit operations, under these operations that I introduced on the previous slide. If you start with two SLH models, you concatenate them. It's pretty intuitive what happens. You just kind of stack them. There's no interaction. However, if you feed one into the other, yeah, you expect that something like scattering in from the right would now scatter first through S1, then through S2. And there's also the output of L1 gets scattered by S2, so that is represented in the updated coupling vector. And then on the Hamiltonian level, there's also an interaction that's being introduced. And yeah, these are really convenient rules, and I think I will briefly show you how you can experiment even more. And feel free to interrupt me and ask questions, because it's supposed to be interactive, at least these coding sessions. So what this package provides is a whole library of different little component models. And so here I've imported the beam splitter model, a phase model, a coherent displacement, and a two-port Kerr cavity model. And so I can interact with these objects in different ways. So I can either visualize them, I can show their SLH model. Some of them accept parameters. So the beam splitter actually also accepts a parameter, but it has a default value for the rotation angle that yields this 50-50 beam splitter model. So none of this is very surprising, I think. Some important helper systems to close the algebra are an identity system, where it's the trivial system, so to speak, of n channels. It just passes the signals through. And then there's also a way to construct permutations of channels pretty easily, but I'm not going to go into that right now. So then to get to the actual circuit algebra, you can in code just write one object and then this left shift operator to do the series product. So that's just been overloaded for those objects. And yeah, you can visualize again, you can compute the SLH. And now you see feeding a laser source through a phase shifter produces exactly what you think. The overall scattering element will still be the phase shift, because something coming even from the, I guess here from the right, or in the other notation from the left, or here from the right, would still pick up that phase shift. But now the coherent amplitude has also been shifted in its phase, right? Okay, and then you can concatenate things. So we can concatenate these two objects with a trivial scattering system, which looks like this. And now we're in a position to actually feed this into a system that has more than one port, right? Before that, we couldn't do this. So that's what we're going to do now. And again, I think the more complex your circuit algebra expressions get, the harder it is to see what's really going on. And so these visualization tools are, for me, they're completely necessary. Okay, and then, right, so now we're going to do something slightly less trivial. We're going to do feedback from a Kerr cavity that is driven by a laser source through a phase shift to its second port. And if you look at the circuit expression that I put in, the feedback is the outermost operation, right? So first I added concatenated the laser source and the phase, fed the combined system into the Kerr cavity, and then I did a feedback from the first output to the second input. However, the thing that's represented here is not that. Like here, if that were the same thing, then the W should really be up here. And so what's happened here is that the circuit algebra expression actually was rewritten or simplified, right? So many of you, or probably all of you, have used Mathematica before. There's a lot of implicit expression simplification going on all the time when you use it. And this is the case here as well. Especially with feedbacks, you want to resolve them as much as possible because they make the analysis, I think, the hardest. Because with pure series and concatenation, it's pretty easy to intuitively just guess the final L, S, and H. But with feedback, there is some operator inversion, or at least numeric, like number inversion, that goes on that is much harder to intuit, I'd say. Right, and then you can compute the final SLH model for this thing, and look at the individual things. All right, so back to the presentation.
Two quick questions.
Mm-hmm.
So, from a sort of design perspective, it's usually a lot nicer to work from a transfer matrix picture than from a scattering matrix picture.
Yeah,
Does
but
your software have an easy way to move between the two?
for linear systems, yes. But I mean, obviously, for nonlinear systems, you can't.
I mean it slightly differently. If I were to specify the boxes in their connections using a transfer matrix picture, can I then quickly move to your other?
So the conversion back from a transfer matrix picture, I think, is not unique. So I could implement something like that very quickly, but it's not part of my usual workflow. Usually I go the other way. I start with an SLH model, derive the linear model from it, and then, because I want to linearize about different points and so forth. So I think it's the more natural way than doing it in that direction. Yeah. Other questions? Okay. All right, sorry, that was actually the demo. Okay, so now just a quick slide on the semi-classical approximation. This here is for a Kerr cavity, and what we do is we take the master equation for a kernel linear cavity, compute the Wigner transformation of that master equation, which then maps to a partial differential equation for the Wigner function, and then we drop the third order derivatives because we have a good hand-wavy argument for why those don't matter when the coherent states are larger than, let's say, implying a few tens of photon. So this is something we haven't actually proven rigorously, but just tried out in many simulations. Another source on that is actually an older paper by Carter from '95. And what this allows you is then, so in this form, the partial differential equation is now a Fokker-Planck equation. And a Fokker-Planck equation can be sampled from, or the distribution that it's for can be sampled from by doing stochastic trajectories. And what the big advantage of this is that the numerical effort of simulating these is now usually linear in the number of systems in your network, because usually the connection matrices A are very sparse. And so you really only have a complexity proportional to the number of modes. And that is something that scales up numerically quite well. So obviously there has to be something missing compared to the full quantum evolution. But for the parameter regimes that we're working in, we found very good agreement. So this was work done together with people at Hewlett-Packard. And as I said, Charles Santori will be talking next Thursday, and you can quiz him on the details of this. Right, so an interesting thing to point out is also that this was only for Kerr cavities, but this is very easy to extend to Chi2 type nonlinearities. And actually, my lab mate Ryan is now working on extending it to free carrier type nonlinearities as well, where there actually doesn't exist a nice SLH model, because those have infinite numbers of degrees of freedom So it's really hard to do full quantum simulations of these. Right, and then one other thing I'd like to point out is it's equivalent, so this looks very much like the ABCD formalism, except there's that nonlinear function that gets added to the evolution of the modes. So you can just compute, however, the updated A, B, C, and D for a whole network in the same way as you can for linear systems. Or you could just first do everything in SLH, compute the full SLH model, and then again translate that over into this Wigner-based description. So they're equivalent in that sense. Or yeah, not quite, but there's a commutativity of those two things. All right, so I'll just list some things that come up a lot in my work that are really important for designing your system. So the first thing is finding classical fixed points of your system. Even in a full quantum simulations, it can be very useful to displace your whole system unitarily to a frame where the steady state has very low expected photon number, because especially if it's not like a bistable state or something, because then you can actually do with a much smaller Fock space. Then linearizing a nonlinear system about such a fixed point, computing transfer functions, doing stability analysis for the linearized model. Carrying out adiabatic eliminations, that's unfortunately something I probably won't get to today, but you can use the symbolic algebra also to help with simple cases of that, especially when you're eliminating just a cavity mode in like a bad cavity limit and maybe some other nonlinear parameter scaling. You can do this pretty easily and again get around the very tedious application of the adiabatic limit theorem, which first you have to convert everything to SLH, then you have to compute the K operator from H and L, then you have to identify the things at scale in some way, and all this can be automated, of course. And the only input you provide is how to invert a certain operator in that expression, and for some cases even that could be automated quite easily. And then finally, of course, simulation, numerical work, where you either simulate the full quantum dynamics, where of course there are different types of simulations, ensemble average master equations, stochastic Schrödinger equations, or stochastic master equations, depending on what measurement situation you're looking at. And we can do the semi-classical SDEs, which I've been doing mostly lately, but I'll talk more about the quantum dynamics because of the audience. Right, so now, just to show how complex the circuits we're working with are, this is what I call an optical perceptron. And what it does is it takes in classical information encoded in the coherent amplitudes of 3 inputs, and really only in the real quadratures of these inputs. So that's something that can still be improved. And then there are 4 in this case, but really n tunable amplifiers, or programmable amplifiers, I should say, that amplify each signal, then they get summed together and sent through a thresholding nonlinearity to produce a state label. So what this thing is, it's a binary classifier for information. Those of you that have ever taken a machine learning class or some stats course have probably already seen something like this. And the nice thing about the perceptron algorithm, which is really used to be a software algorithm, is that it can be trained incrementally. So you present it with training data, and pre-labeled training data, that is, and it'll update its amplification weights continuously by making little jumps according to whether some example was misclassified. And that is, I think, something that maps quite naturally then to a hardware implementation, because you can make small changes to your weights and converge on something that works most of the time. The nice thing about this particular model is that there's no external control required. So all the non-signal inputs are constant input fields. And I want to claim that this is the first proposed all-optical system capable of learning in some sense from data. Right now, the model is based on both Chi2 and Chi3 nonlinearities because that makes it easier to design. But Chi3 alone would be sufficient, and I think you could do it with free carry nonlinearities too, although it would become harder to design and a little more messy. And here's an example of how the system evolves. So the weights are really encoded through these phi parameters. And here's a time sequence of like in continuous time, the system being presented with different data points that are pre-labeled. And up to the blue line, the system is in training mode. That means the t input is high, and there's a control feedback to the weights to update them. And so the red line is the weight that it should have, and the black line is the the red line is the true class label y, and the black line is the estimated class label y hat, which of course isn't really discrete because it's the output of a continuous system. But you can see that initially the system misclassifies, but then pretty rapidly converges, and then it gets almost all the examples right. So now to show you again the complexity, I'll go into what the individual component models are. So the synapse consists of the following. You have two Kerr, I call these symmetric Kerr nonlinear amplifiers, where one of them has a positive gain, one of them has a negative gain, and they are configured to have the magnitude of their gain anti-correlated. So either the positive gain is high and the negative gain is low, or vice versa, and that means you can range between approximately 1/2 the maximal positive gain and 1/2 the maximal negative gain. And the thing is driven by something that is really like the trick of this construction. That is something like a tunable a laser source that can be programmed to have a certain magnitude, and then by varying that magnitude, you can change the bias inputs to these amplifiers, and the bias inputs to these amplifiers determines their gain. And then on the left side, all this is really just necessary for training the system. So these are more like binary logic circuits, somewhat closely, like not the same, but related to stuff that we've shown before in our lab or proposed before. Right, and then so overall, this system is a programmable gain linear amplifier. By that I mean you don't provide an extra input to specify the gain, but the gain gets stored and remains fairly stable over some time period. This system depends on 8 nonlinear optical resonators, something like 20 beam splitters if we look inside of these components, and about 50 internal connections. So doing all this by hand with an SLH algebra would be quite tedious, though possible, but it would not allow us to like rapidly change something, try something new. Right, and then even at the end of that, there are a lot of design parameters that are also, if you were doing full quantum simulations for even part of this, and you had that many parameters, it would be pretty slow progress because you'd have to wait so long after each simulation. So having the semi-classical approach will help us a lot, or has already helped a lot. Yeah?
So I'm kind of curious because you're applying this in the semi-classical regime.
Right.
There's a very canonical semi-classical system,
right,
which is nonlinear,
right,
which is the laser.
Right, okay.
And I'm kind of curious how well your approaches work for describing all this beautiful physics that we associate with how lasers behave.
So I guess it really depends on what sort of laser. You can have something, so if you're describing something that is pumped electronically, I wouldn't know how to describe it with our framework, but you probably could come up with a semi-classical model for it. But I wouldn't know how to derive it from an SLH model. Let's say that, because I couldn't write down the SLH model. But this thing here is actually just a non-degenerate optical parametric amplifier above threshold. And what happens is you have a pump input and 2 vacuum inputs for signal and idler. And if you go above threshold, signal and idler spontaneously start putting out power, right? And their phase, while correlated with each other, is independent of the pump phase. And that's why you can have a tunable laser source, or at least something that's not tunable in amplitude, but tunable in phase, that remembers its phase if you configure it correctly. And if you then mix it with a constant offset, you can get something that has also a tunable amplitude, or remembers its amplitude. That's what I said by we have our own kind of like laser source in this circuit. But it's not like another kind of laser.
In other words, at the moment, you don't know whether or not this model can reproduce canonical laser physics.
Yeah, I wouldn't want to claim that, but it's a known nonlinear optics model, and it's being used to actually in our lab right now to generate light at frequencies that are otherwise hard to attain. So yeah, I could like come up with an idea for integrating some laser model in the circuit, but I think right now this works pretty well and is a three-dimensional model, three complex amplitudes, and I think any description of a laser, I think would be a little harder, but I'm not sure.
The way I might start that is your gain medium in the laser would be some nonlinear, would be a nonlinear input-output component has internal dynamics that represent the gain medium, and then the mirrors would both be high reflectivity beam splitters. And the beam splitter would couple between signals that were leaving the laser, and then there would be feedback between the two beam splitters as they go through the gain medium to make it simulate a laser. And each of those three components you could put into an SLH formals and then make a little feedback network that does the routing that happens inside of the laser. So that's how I might start trying to model the laser dynamics.
Yeah, I see this merely as a litmus test, as a statement that this methodology holds up, because you have a set of well-known results in laser physics.
Yeah.
And I see no particular reason I can't put it in SLH picture.
Yeah.
And in doing so, I should be able to reproduce those effects.
I would imagine that would happen, but I guess it hasn't been a priority for them.
Yeah, no, I'm just sort of curious why not, actually, because in some sense, this is a really simple but nonlinear and well-understood system.
Well, it's been tested in other contexts that.
I understand. I mean, a reasonable answer might be because time delay is hard in SLH. And that's a big part of laser physics.
You can manage it.
You can do time delay pretty well over a limited bandwidth.
No, I'm just sort of trying to understand why not. It sounds like.
Yeah. No, so I have studied models that are self-oscillating and stuff like that, but I think the thing I never did was model some kind of non-optical pump for the laser, and I think that would be an important thing to do. Yeah.
Can you say a bit more about, say, the classical side of this? So, are you trying to implement some method from learning theory for classification? Or how would you?
Right. So
how would you describe, without the quantum stuff going on?
Yeah, the motivation for this is to create ultra low power kind of analog circuits to do signal processing. And that can be reconfigured, so that are not universal computers, but that can be reconfigured for different tasks. And the extension to making the signals and also the energy scales at which these components operate more quantum is something we're very interested in. But I think we're starting with the semi-classical side just to understand that really well. And then we will try to come up with a tractable model that can be studied in the full quantum regime. Yeah, I think this, if it turns out, so I'm not done with the analysis of that yet, but if it turns out that the energy per computation, per classification of something is way lower than for electronics, and if the thing can be scaled up to very large input dimension, it could be a useful circuit for somebody to actually build to do something. That's, I think, another motivation for going to analog style computation is that it gives you maybe a more natural framework for dealing with non-perfect components. So there's been a lot of work in the early days of computing for how to construct reliable, or how to do fault-tolerant computation with really messy analog elements. And that got unnecessary very fast because digital electronics got so great very fast. But people are going back to that. Even in the electronics world, there's a lot of work, I think, in this direction right now. So, right. So now, this will be the model I'll show as an actual case study in the notebook. So, what is this tunable gain Kerr amplifier? It's two Kerr cavities with, as I said before, intensity-dependent internal detuning, and that means the system goes on resonance at some particular bias power and is off resonance before. And there's a certain bias power range in which it's close to resonance, and that's where its response to an external signal is the strongest. And if you take a single one of these and you send in some bias and combine it with the gain, so if I just left out this lower circuit, it would already have an amplifying response, but I would have to set the interference or configure the interference very carefully for a particular gain. And this construction is really nice because if you choose the phases correctly, so these are supposed to be evanescent coupling beam splitters, if that wasn't clear. Sorry. So these are like beam splitter models, but they look a little bit like they would look in a nanophotonic implementation. And these are nanophotonic ring resonators that are also evanescently coupled to the waveguides. And so this interferometric configuration allows you to always isolate the bias and the signal input. And furthermore, it achieves that the bias and signal arrive at these two cavities. So the bias, in both cases with the same sign, and the signal with opposite signs. And so that allows you to actually separate them back out over here. And that allows you to overall isolate bias and signal like paths through the system for any bias input. And that means for any gain that you choose by configuring the bias, you will still have an amplifier on this upper connection. Yeah, it's important. This is a phase-sensitive model. To get a phase-insensitive gain, you'd have to work with a more complicated system, or of course use an OPO model. Right, so varying the bias power changes the gain. This construction doesn't just work for Kerr-type nonlinearities. It works for any even lossy thresholding type nonlinearity. And the beam path separation that I mentioned works when the two systems are pretty identical in their response. So that's the engineering challenge, but that's what I assume. And then it turns out that for the Kerr model in particular, if there's no internal cavity loss, and at the correctly chosen bias input, the system is a perfect squeezer for the signal input. Obviously, it saturates for large signal inputs. So you need this condition to be true. Oh yeah, and then another nice thing is that this output depends on epsilon only. So the linear output, and then the next contribution is of third order because the second order also gets subtracted with this configuration. Right, so now the computational workflow. So first, we specify the network through some netlist. I'll show you how. We then convert it to symbolic circuit algebra expression. We convert that to SLH and analyze. So I wrote this up here. You can actually already do some analysis on the circuit, on the level of the circuit algebra. I think this will be very useful for very large networks where you know that a particular sequence of models always has the same adiabatic model reduction associated with it. So in that sense, I think if you scaled up something like the QEC network that Joe's been working on, yeah, then I think that would be a useful thing to do. But then you can analyze on the level of operators. And finally, you can fix the numerical parameters, convert it to numerics, and simulate things. Right, and then because usually you don't get it right on the first time, you go back to any of these steps. So quantum hardware description language. By using an existing standard for electronics, we were able to just use existing tools for electronics. And this is an open source schematic capture tool called gschem. And so what we've done is we've created little component symbols. And with that, you can just construct your circuit. You can then, you can draw lines between them, connect ports, and so forth. And you can assign parameters. So the top level system has a certain name and a certain set of parameters it depends on, and these can be passed through to the components inside the circuit. And then you designate overall global inputs and outputs with these pad symbols here. So these are inputs, and then over here are outputs. So this has worked reasonably well. The only thing about it is that it's not easy to install. So I'll show you at the end how I address that. So this model is stored in a schematic called like SCH ending. And you can then convert this to a QHDL file, which we can look at. So a QHDL file is really just what I told you about in the graphical editor specified in text. You have a global interface to your system, some parameters, some ports, and then the architecture first again defines what types of objects can appear in it, and then it specifies interconnections and mappings between parameters. So if this is a little fast, I'm just running out of time, so I'm going a little fast, but we can look at this after the talk maybe. So then this thing gets translated into actually a Python module. So I do most of my work in Python, some stints in C and some other languages. And then you can import that. And let's look. So this allows you to actually look at the generated source code of the Python file. And it's in some way similar to the QHDL, but now what you see here is a circuit algebra expression that's already been simplified as much as it can, that it then returns when you try to use this model. And what's nice is that you can kind of unpack what's inside this box. So from just starting with the model, it just looks like a 4 input, 4 output system, but then you can reduce it to its expression and keep reducing it to break it apart and try to really trace the series products in this thing. So, all right. Yeah, so here, again, this is what a QHDL file looks like, or VHDL. It's a subset of VHDL. We've defined almost no extra keywords, and I think those that we have are allowed to define. It allows for hierarchical design, as circuits in general do. Existing schematic capture tools can be used to generate it, and it makes it easy to share your models with somebody else, because you just have to send them a text file, provided both have installed the software. Okay, so now the next thing is QNet. QNet is then the symbolic algebra package that you've already seen in action, but that's doing the real work. So I'd say QNet, like in terms of code, is way bigger than the QHDL parser and so forth. So what it does, it implements symbolic algebras for Hilbert spaces, tensor products. This is very trivial, very easy. But then operators on Hilbert spaces is probably the most involved one. And then even simplification rules and so forth for circuit algebra elements and SLH models. And then finally, I have 2 extra algebras that I wrote because after these it was really easy. A superoperator algebra and a Brockhead state algebra. So I don't really use them on a day-to-day, but they're nice. They're nice toys. And then I think it would be very easy to write new types of algebraic things like a quantum Ito calculus would be very easy for me to implement if there was, or for somebody else to implement if they got around to looking at this code. So some more examples of what QNet can do or how I would use it. So I'm now going to import the model that I actually just created in the last step. And the model has these certain parameters that I then define as symbols. So I'm actually using SymPy, which is a very nice symbolic algebra package already existing in Python, but I only use it for the scalar coefficients of operators. It does have a quantum operator algebra, but I guess I decided to roll my own for that. Yeah, so this is again the model, and now we can start adding inputs. Look at the resulting SLH. We can derive the symbolic equations of motion for the mode operators of the system. So yeah, I write this a little sloppily like this, but it's because I can't easily add a D2 to the other terms. So. And yeah, you can see, so this is really helpful because most often intuition is more easily developed by looking at the Heisenberg equations of motion for the modes. That'll allow you more easily to construct something, at least in our applications where we're more focused on input-output behavior rather than doing quantum information things right now in the internal state. At least my work is not very quantum at the moment. Yeah, and you can use the superoperator algebra to derive a Liouvillean. So if you've ever used the quantum optics toolbox, you'll know these sPost and sPre commands. And what they mean is sPost is a superoperator that applied to another operator takes what's in these brackets and multiplies it by the right. And sPre does the same thing, but from the left. And so these two are able to generate all, I guess, finite length sums of superoperators. And we can check that this superoperator applied to rho gives the same as the computed analytical master equation. And that is this. So yeah, that works. And then, yeah, as I mentioned before, so you can easily compute the ABCD matrices. So in this case, only for passive systems where it's not doubled up, but it would be very easy to implement the doubled up version as well. And other things that I find useful is to just displace, for example, the cavity mode operators in their Heisenberg equations of motion by some constant amplitude, and then take the 0th order term in that equation of motion, solve it, because that's just a scalar equation, or set it equal to 0, solve that equation for example, the input field, and that gives you an input-output relation very easily. And that can then help you translate your system unitarily to a frame where, if it's stable, the ground state has very low photon number. Yeah, and then, yeah, this is what I show here. You can easily then plot and manipulate input-output relationships. It's quite convenient. So this is a new edition of this tool. I'm using the IPython notebook, which allows you to have little sliders, as Mathematica and MATLAB already have supported for a while. Yeah, and so this is what I just mentioned. You can transform the model to a frame in which the steady state is close to the vacuum state, and that would then be this model. And you see now it's changed from a Kerr Hamiltonian to having all kinds of additional lower order nonlinear terms. Right, okay, so that is QNet. So how does the symbolic algebra actually work? Well, so for any expression, you should think of a graph or a tree. The outermost operation is the root node, and so in this case, that's a product. And the arguments are just little leaves on that. And then if the one argument is again an expression, then you can just look at it like this. And so when you do expression simplification, you have to do pattern matching and replacing on trees. And yeah, that's really what you have to get into if you were to extend QNet for your own algebraic simplifications. It's not that hard, but it does take a little time to pick up, I think. Right, and then if you've done a good job, then your rewrite rules lead to something like a normal form. So that means two expressions that look different but are equivalent mathematically get translated to something that actually looks the same. And that is important if you want to cancel terms in your expressions, because otherwise your system won't know they would cancel, right? So you need to have some kind of convergence for these things. And that's a pretty delicate art, especially for the circuit algebra. It's actually not perfect yet, but it works fairly well now. Oh, well, maybe I think I already did that. I'm not sure. I think I'll skip that. And skip ahead to the numerical simulation analysis because we're close to running out of time. Yeah, so now this is an example how you would go about constructing an SLH model from scratch. So here I define symbols, numerical symbol or scalar symbols. Then I define the H, the L, and the S. And so ADAG or destroy one would mean create an annihilation operator acting on the degree of freedom labeled by 1. And so that makes it very easy to work in tensor product bases because you can just define operators as acting non-trivially only on very distinct spaces. And yeah, and then you just use the normal mathematical operators to construct your overall circuit expression. Let's run this. So yeah, this gives us a Kerr type Hamiltonian that is driven by an input. And again, Heisenberg equation of motion, or the SDE. Displacing, I showed this before, so I'm not going to, so for the more complex model. Then we convert that to a numerical representation. So now it actually gets converted to sparse matrices. I'm using Qtip to do this. Originally I had my own code, but that was a lot of code to maintain. So now I'm using Qtip, which is a really nice package developed by Robert Johansson and Paul Nation. I think they started when they were at Recon, but now Paul, I think, is in Seoul or somewhere else in South Korea. Yeah, and then we can do stuff like finding steady states. And here I've already constructed a model that'll be nearly bistable because I'm also going to do a quantum trajectory simulation. So we can now again compute the A matrix, or this is actually now the doubled up A matrix for a linearized about a certain point, right? So this is not necessarily around the vacuum. And yeah, it's not represented as a matrix really, but yeah, you should think of this as being below each other. And yeah, you can then very easily create a function that just spits out the numerical matrix for some values for these parameters. And again, interact with that, make a little applet that shows you exactly the stability of the semi-classical model. And so yeah, you can play around. I think, so if you can't tell, I think this playing part is really important. And yeah, a fun part in the work. And when you have that many parameters, I think it's actually the only way to move, because it allows you to explore kind of the parameter space more intuitively. So we don't have actual experimenters knobs, but this comes as close, I think, as we can. Obviously, it only works for stuff that can be solved that quickly. And then finally, a quantum trajectory simulation. Yeah, this will actually take a minute or so. So maybe I'll go back to this at the end, and then we can continue with this. Right, so then there are semi-classical solvers that Ryan and I wrote that are not perfectly interfacing with QNet yet, but will very soon. And yeah, once you've converted to ABCD, it's very easy to interface with control theory packages. Yeah, finally, somehow I'm out of order with this thing. Anyway, let me just show you this other thing first. To drop the requirement of having this schematic capture tool, I wrote this thing that actually works inside this notebook. So what you see here is not just an image, it's actually an interactive applet where you can you can add components, you can connect them, And this will make it very easy for us to also do things like bidirectional ports, or maybe even, at least like in the circuit, specify classical feedback connections by having additional like electrical signal lines or detector symbols. I think obviously the dynamical simulations, the code for that still has to be written, but at least you can start describing stuff this way. And yeah, this is also nice because it's SVG, so vector graphic. It's nice to export for publications. Yeah, so that's about it for the tools. Let's see if the other thing is finished. Nope, not yet. Okay, I think I have a couple more slides. So yeah, I think I've proven that designing quantum feedback networks is much easier with a tool like this. It helps with all the tedious and simple analytic computations, like just canceling terms, reordering operator expressions, commuting things with each other, applying commutator relationships. It then makes it easy to interface with numerical backends for the simulations, for dynamical simulations. And once I have this new circuit editor that I just showed at the end, integrated nicely with the rest of the package, you won't even have to worry about installing a ton of open source software that's hard to compile or whatever. So the dependencies will be very few and they will be very easy to install. So you can get started doing this. A nice other thing about this notebook is I could have been running this on our machines back at home because it's in a browser, and so you can easily do an SSH tunnel. The data that is being transmitted is not like a GUI or like X Windows where you have a huge lag if you're doing this over a network, but because this is just text that's being transmitted, you don't have any latency. So it's a very nice tool. If you're not using Python yet, I recommend that, and if you're not using the IPython notebook, then you should really do that. Yeah, and then plan features for the future. Like I said, I'll improve the circuit editing interface, add QHDL file export and stuff like that. Better integration with the semi-classical codes that we have, and maybe that's something Hideo and I have been thinking about for really high-dimensional problems where the Lindbladian or the Hamiltonian would never fit into memory. Do something like a symbolic fast numerical implementation of large linear operators, where you only need to store the state in memory and not the operators. Yeah, and if you have other ideas for QNet, I probably won't add them myself if I don't also need them, but I'll definitely help you if you want to add them yourself. Yeah, and if somebody, or if a sufficiently large group would like to maybe help to install this next week sometime, I'd be happy to do some kind of tutorial session at some point. I think John also thought this was a good idea. Oh yeah, and then finally, acknowledgements. Thanks for inviting me. This was great. Then all my lab members, Hideo, and all the alumni and visitors that we've had. Everybody that's developed the packages that I'm relying on, and then the foundations that finance me. All right, thanks. Any questions?
Maybe the trajectory circuit.
Yeah, I hope it ran well. Let's see. Oh, I think so. Oh yeah, there it is. So as you can see, so I ran 20 trajectories. This what's plotted here is the expected intracavity photon number over time. And while it's not, I think it's visible that it's bistable, right? So it seems like there's a stable, it's metastable branch up here, and there's some other metastable state with a low number of photons. To actually show this, I could do a histogram or something, but.
Is this time?
Oh, right, this is time, yeah, sorry, this was a little sloppy. But yeah, that's time.
Shouldn't it spend some time in the high energy and then the low energy? Why are they?
So these are 20 trajectories. If I just plotted one of them, they would, yeah. Let's see. Yeah, so this would be a self, right? Let me. Yeah, so now you can see it. But yeah, this is invisible, so yeah, that's no good. All right.
Questions?
Yeah.
For the tunable gain curve amplifier, so are these input-output states or coherent states?
Yeah. Well, so they don't have to be, but they have to be nearly coherent. Yeah. Yeah. I think it might be possible to go to analyze the system and see what happens if the signal isn't a coherent state, if it's a more quantum-y state. But yeah.
As you mentioned that the ideal case it corresponds to a perfect squeezer.
Right.
Does that contradict with the statement it's a coherent state? Oh, you mean squeezer compared to dissipation, combined with the dissipation that you go to?
I mean, so there is very little dissipation in the model. It's it's really if you look at the linearized model, it's exactly the same as a degenerate OPO.
Oh, you mean
In that sense, yeah. I mean, obviously there's really a nonlinearity, so it's not a perfect squeezer. But to the extent that the OPO model is, or maybe a little bit less so, it's a perfect squeezer. The OPO also has only finite bandwidth, and if you go to high enough powers, it's not going to be a perfect squeezer, right? Okay.
One question.
Yeah.
Suppose I know SLH, I want to learn your software. How long will it take?
Do you know Python already a little bit?
No.
Okay, it's very close in syntax to MATLAB. If I would probably put a student to work on it first, have them pick up the know-how, and then teach the rest of the lab. In our lab, people that have MATLAB experience have started working with this within weeks. So it's not. I mean, you will have to invest a couple days, I'm sure. But yeah, I think it pays off very rapidly if you're doing anything like this. Yeah, you save a lot of time at the end.
Can I have more questions? Can I come back to the learning problem? So just I'm trying to understand it. So in classification, usually you have say 2 distributions and you get some samples from them.
Right.
Like this.
Mm-hmm.
And then you want to classify a new point, and
Right.
the simplest thing would be to draw a plane between them.
That's what this is a linear classifier. It draws a hyperplane between your 2 lobes of data.
So you are basically, so it involves some linear algebra with these input lasers, or
Wait, why is the picture gone? Oh, because of the board?
so yeah.
Oh, I see. Yes, so what this thing really is, is a tunable linear transformation. It's a tunable inner product with one vector. You could make a bunch of these and make a matrix vector multiplication. Yeah, that's basically what it is. So you amplify, so you multiply an input by a value of your choice. So far it's phase sensitive, but I think I already know how to make it phase insensitive. But yeah, that's basically what we're doing. And
Why do you need nonlinearities? Or
to make a linear map, you don't. But to make a tunable linear map, you always need nonlinearities, right? If you can't change the coefficients, then you're not learning.
and the final measurement is some kind of.
Yeah, it's just
Homologous
discriminating
stuff.
between 2 power levels then. Yeah, so that should be, or you mean this final thresholding? Yeah, this is just a system that has a very strong thresholding response around some bias input. And so, yeah, you can then clean it up to be more like a real logic level or something quite easily with some more fan-out stages or something. But I haven't, so right now this is also not the most scalable architecture because as you can see, it's feeding this estimated state label for the training back through all the systems in sequence. And if all of these require a certain number of photons to update their state, then the last system will take much longer to get that update. And so when I scale this up, I will most likely add a bunch of fan-out stages to this estimated state label and then feed that back. So that, I'm not sure how easy that would be with a quantum, like a more quantum version of this, but yeah, I'm curious to see what happens when I look at it. Another thing that Nina and I are working on is to extend this to a nonlinear classifier, where the separating surface between your clusters of data are not is not a hyperplane, but something more general. So.
All right, so if there are no more questions, let's thank the speaker again.